Alright, we're trying out a new software today for 6.2, which is graphing quadratic functions. We talked about the difference in a function and a relation, that all functions were relations, but all relations are not functions. And we talked about the vertical line test, a way to tell from a graph whether something was a function or not. And we talked about parent functions. And what I want you to know right now is we're going to regraph the parent function of a quadratic, and that's mostly what we're going to be working with for the next few weeks. But we're also going to talk about how some of the same things apply that we're learning to absolute value and square root functions when it comes to translating them or moving them on a graph, because it's a lot of what your next CBA is going to be about. But I remember I told you to pick some points when you're graphing if you're not sure what it looks like and if you don't have the calculator to use as a tool. So you pick points, and we can do that by just going along and filling in this table. So we can say go from -3, -2, -1, 0, 1, 2, and 3. And y is x squared, so the y value would be -3 squared, or 9. And then 4, 1, 0, 1, 4, and 9. And when we go over here and plot our points, we can go here. Let's see if we can make this bigger. Whoop, a little too big. Okay, and we can plot our points. We have points at 0, 0, 1, 1. -1, 1, +1, 1, -2, 1, 2, 3, 4, and +2, 4, and -3, 9, and +3, 9. Okay, and then we can draw our line through these. Hopefully you'll do a little better job than that. Whoops. Okay. And that's our basic parent quadratic function. We reviewed that the other day. At rest, there has a vertex. In this case, it's a minimum. When a parabola opens up, it has a minimum point or a low point for its vertex. If it points downward, it has a high point or a maximum for its vertex. And we're going to talk about vertex form today. So that is our basic parent function of a quadratic. And let's close this up and move it over. Okay. Now, I'm going to switch so I can hopefully get the mouse back and move the page down, so these lines are going to go away. So, and we'll move this down, I hope. Oops. There, we want to stop at translation form. Okay, right there. Okay, so let's get our drawing tools back. This is basically translation form, also called vertex form, because from this form you can read the vertex. So in other words, this is also called vertex form, and that's pretty bad writing. But anyway, vertex form. And the reason is because you can read this vertex, HK, right from the equation. See where a minus h means that h is the x value of the vertex, and right here, and plus k, that's the y value of the vertex. Okay, so we read the vertex from this equation, first thing you do, and then you can plot points to graph it. And we will learn later how to show how these shift based on how they're in the equations. But what we look at first, and it's important to remember that when you have x minus 5, okay, squared, plus k, that's the form plus -8, that would give you what we see there. And so the vertex is +5 and -8. And so it looks as though you change the sign, especially if the one inside the parentheses, when really you don't, because that's the form that it goes into. So we go over here and we put our vertex at -5, at 5, -8, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8 right there. Okay. See if I can get that a little bigger without trying to select everything. Okay. So that's our vertex form, and I tend to call it vertex form rather than translation form. Now we can pick our x's. Now we really want to pick them right around the vertex rather than, since the parent function had a vertex at 0, but this one has a vertex at 5, -8. So let's go first 1 on either side of that, which would be 4 is 1 less and 6 is 1 more. And then we can go 1 more on each side, so that would be 3 and 7. And we could go 2 and 8 if we wanted to get some points on either side of the vertex. Now I'm going to erase some of this to get it out of the way because it looks a little messy. All right, so let's look here. We're going to put x into this form, so we have 2 times 4 minus 5 squared minus 8. 4 minus 5 squared is -1 squared, or +1. So 2, or that was going to be +1. 2 minus 8, that's going to be -6. So at 4, we're going to go to -6, which is right there. Okay. And then at point 6 times, we have 6 minus 5 squared minus 8. That's 1 squared. 2, that's also -6. So 1 over from the vertex, we went up 2 on each of these. And we're going to see, as you notice, that this parabola is symmetric about this axis of symmetry, which runs right through the vertex and goes right down here through the vertex. Straight line, if you thought of a vertical line going straight through the vertex, that's your axis of symmetry. But let's look at 3. We have 2 times 3 minus 5 squared minus 8. 3 minus 5 is -2. -2 squared is 4 times 3 is 12. 12 minus 8 is +4. Okay, so at 3, we're going up here to +4. I'll make this a little bigger. 1, 2, 3, 1, 2, 3, 4. And I'll erase my axis of symmetry marks because they're a little confusing. Okay. And we would expect then, if this is symmetric, that we would also be here when we go to 7, we'd also be at 4. So let's double check and see that we are. Okay. So at 7, we're going to put a 7 in here instead of a 3. Actually, that should have been a 2. So that's a little, I think I was wrong because I put the 2 there instead of a 3. So we'll put 7 minus 5, that's 2 squared. 2 squared times 2 is 8 minus 8, so that should have been 0. This should have been 0, and this should have been 0. So let's move over here. And these are at 0. And we've got to get rid of my mistake. Okay. All right, so now let's look at 2. 2 times 2 minus 5 squared minus 8. That's -3. That's 9 times 2 is 18 minus 8, so that's going to be 10. And if that was 8 instead of, if that was an 8 instead of a 2, that's 3 squared. That's 9 times 2 is 18. 18 minus 8 is also 10. So we're seeing this symmetry as it's around that it's symmetric about that axis of symmetry. So let's put in, we're going to go over here to 3 and up to 10, and we're going to go over here to 8 and up to 10. Now you notice that for a few points this parabola is much taller and steeper than our parent function. That's because of this 2 right here. This 2 right in front, right here, is what makes that taller and steeper. another. It's a horizontal compression or a vertical stretch, and you may have seen those on your benchmark that you just took. You just hadn't gotten to this yet, but that's the idea. A horizontal compression is the same as a vertical stretch, and a number in front of this, that's what the A represents in all these formulas that we're going to learn. That A in front, that number in front, the coefficient in front of the X is going to tell you whether it's narrow or steep or short and broad. All right, I'm going to move up, so I will be erasing these values and go to the next page. Okay. So we can move to the next page. Okay. And make this a little bigger so it's maybe a little easier to see. Can't do too much. All right, so now we've got another vertex form. And this time we have a negative one, x plus 5 squared. Now you'll notice right here, there's no k, is there? There's no plus some number. So what we have with that case, we have plus 0. If there's nothing there, it's a 0. And so remember to get that plus, though, because it's x minus h, to get the h, that has to be to get the plus, that has to be a negative 5 squared, and then the plus 0. So our vertex for this one is negative 5, 0. Okay? And so for our graph, I'll make that a little different. Let's go to negative 5. Make it a little bigger so we can see it better. 1, 2, 3, 4, 5, and 0. Okay, so we have negative 5, 0. Now let's pick points again around the vertex. Now, so on either side, we have negative 6, okay, so we have negative 6, and on the other side of that we have negative 4, and we have negative 7 and negative 3, and we could do negative 8 and negative 2 if we wanted to. All right, so let's plug these in to our equation and look at what we have. We have, all right, negative 1 times negative 6 plus 5 squared plus 0. So negative 6 plus 5 is negative 1. Negative 1 squared is positive 1. But positive 1 times negative 1 then is negative 1. Okay, for negative 4 we have negative 1 times negative 4 plus 5 squared. That's going to be positive 1 squared is 1 times negative 1, so we have another negative 1. Again, seeing this this idea of symmetry about this vertex. So we have negative 1 times negative 7 plus 5 squared. That's negative 2 squared, which is positive 4. And 4 times negative 1 is negative 4. Okay. And if we have the negative 3, we end up with positive 4 again. So we end up with the same thing as we did there, or a negative 4. And for negative 8, we have negative 8 plus 5 squared. That's going to be negative 1 times, that's negative 3 squared, which is 9. So that's going to be negative 9. And we'll find out with that same idea of symmetry that the negative 2 will also give us a negative 9. So let's go ahead and plot some of these points. We have the negative 6. negative 6, 1. And we have the negative 4, 1. Okay. Then we had at negative 7, we went to negative 4. And at negative 3, we went to negative 4. And at negative 8, we were down here at negative 9. And at negative 2, we were down to negative 9. And so we can see, whoops, kind of got off that line a little bit, that our parabola looks like that. Okay? For that particular vertex form. Now let's move on. And move up. Okay. And go to another vertex form. And then we'll start root form. So let's make this a little bit bigger. Get it where we can work with it a little more. Okay. So in this one, there is nothing in parentheses with the x. Remember, our basic vertex form is y equals x minus h squared plus k. Okay? So the 3, well, that didn't work out very well. Let's do it again. The 3 is the plus k. That's that. Those match. There's nothing in parentheses with the x. So what we'll do is we'll write this. That means there must be a 0 there. So let's rewrite it. Y equals, whoops, we want the negative outside because we don't have a negative x. Negative x plus 0 squared plus 3. So now, reading our vertex, it is 0, 3. Okay, so we can put that on our graph at 0, 1, 2, 3, right there. Okay, and then pick around, that's at 0, so we can go negative 1, positive 1, negative 2, positive 2, and negative 3 if we want to. Okay, so now let's put it in our negative x squared plus 3. All right, so negative 1 squared plus 3 is, that's going to be positive 1, but it makes it negative. So negative 1 plus 3 is going to be 2. All right. And 1 squared made negative plus 3 is also going to be 2. If this is negative 2 squared in here, that's 4 made negative plus 3. That's negative 1. Positive 2 squared will be 4 made negative plus 3 is negative 1. And 3 squared is 9, made negative is negative 9, plus 3 is negative 6. And we would expect then that the corresponding point on the other side of the vertex would also have a negative 6. So let's look at our points and look at our parabola. We've got this, our point here that we've already graphed. And then we see we have negative 1, 2, right there, and 1, 2, right there. Okay. Then we have negative 2 and positive 2 are at negative 1. So right there and right there. And negative 3 and positive 3 will be at negative 6. 1, 2, 3, 4, 4, 5, 6 right there, and right there. And our axis of symmetry, here's our parabola going this way. Okay, and our axis of symmetry, if we were drawing that, is right here on the y-axis. And this parabola should show to be symmetric about that. If I drew the points very carefully, it would be symmetric about that axis of symmetry. We also notice here that the negative, right here, that negative number, makes it open downward. If you looked at the previous problem, it was also negative and it also opened downward. Now let's move on to root form. Okay, root form is another way to graph a quadratic where we're given the roots. And it's like factoring. When you factor, you end up with roots. Roots are solutions to the quadratic. There's a lot of words that mean the same thing as this word roots, okay? They could be solutions. We sometimes call them solutions. Zeros, because it's where it crosses the x-axis. Roots. Solutions, zeros, and roots of a quadratic all mean the same thing when you're asked to find those. And sometimes we forget that, but they mean the same thing. So, a minus, again, R1, if it's minus, R1 is going to be positive. So, the roots are at 3, okay, which is 3, 0, if we're writing it as a point, and negative 1, 0. Okay? So we can put those points on a graph. It's where it crosses the x-axis, so it crosses at 3. Okay, at 3. And at negative 1. Those are your two roots. Now what we're going to learn, what you need to know about the vertex, since there's this idea of symmetry, the vertex is halfway between the roots. And that's a very important fact. It's halfway between the roots. So we can do a midpoint formula, basically, which is 3 plus negative 1 over 2. So the x value of the vertex, which is also the axis of symmetry, is 3 plus negative 1 in this case, which is 2 over 2, or 1. Okay? Now, once we know that, it's very easy to get y. We put it back in our function. So y is equal to, we're given this right here, 2 times 1 minus 3 times 1 plus 1. We put the x value in. This is 2. This is negative 2. 2 times negative 2 times 2 is negative 8. So we have a vertex. Now we know 3 points. We know 2 roots and a vertex. So we go over here to our graph. And we have 1, negative 8 is our vertex. Well, we can get a pretty good graph from there. We can look at points between at x is 0 and 2, and we go points past if we want to. So we can find points. Find points you're missing. We have 0 and 2, and then we could go 4 and negative 2, and that would give us a lot of points to graph our quadratic. So let me clear some space here. Okay, so filling in the blanks now with our x, we have 2 times 0 minus 3 times 0 plus 1, which is negative 3, times 1 times 2, or negative 6. All right, then we have 2 times 2 minus 3 times 2 plus 1. 2 minus 3 is negative 1, times 3 times 2. When we solve those, we again get negative 6. Okay, let's make some room for our next calculation. Okay, at 4, we have 2 times 4 minus 3 times 4 plus 1, which is 2 times 1 times 5, or 10. And this should be symmetric. It should be the same. 2 times negative 2 minus 3 times negative 2 plus 1. That's negative 1. That's negative 5. That's going to be positive 5 times 2 is 10. And we can see, because of this being a positive 2, that it should be a little skinnier than a regular parent function, taller, and it will open up because it's positive. So let's graph these. We have 0, negative 6, and 2, negative 6. Okay, 0, negative 6, 1, 2, 3, 4, 5, 6, and 2, negative 6. And then we have 4, 10, and negative 2, 10, all the way up here. Okay, so we have our very skinny quadratic function that we graph. Okay, so let's move on to another example. We have one more, it looks like. Make sure, is that right? Yeah. I have one more example for number 6. All right, we can see right away, as we look at this, that it's going to open down. A negative 1 means it's not going to be a stretch or a compression. It's going to be basically the shape of a parent function, but it's going to open downward, so it's not a parent function, and it is shifted a bit. So we have roots. Now look at this. You notice that these are the same, x minus 2 and minus 2. So what does that mean? Well, that means that our roots are positive 2 and positive 2. It has a double root. And when they have a double root, that means it just touches the x-axis. It doesn't cross it in two places. All it does, it touches it. So our vertex is at 2, 0. So we go here at 2, 0 and put our dot. Okay? And then we're going to need to select points on either side of the vertex in order to completely fill out our graph. So we'll go with negative 1, 0, or excuse me, 1, positive 1, and then 0. And we could even go to negative 1 if we want to. And then we need to go to 3 and 4. And if we wanted to match the negative 1 point, we would go on to 5. So let's substitute in. We have negative 1 times 1 minus 2 times 1 minus 2. These are both equal to negative 1. So negative 1 times negative 1 times negative 1 is negative 1. So at positive 1 and at 0, we have 0 minus 2 times 0 minus 2, which is negative 2 times negative 2, which is 4, times negative 1, which is negative 4. Okay. And at negative 1, we have negative 1 minus 2 times negative 1 minus 2. Both of these are going to be negative 3. So negative 3 times, I should have put a 2 there, sorry. Negative 3 times negative 3 is positive 9 times negative 1 is negative 9. And then if I put a 3 in, 3 minus 2 times 3 minus 2. That's negative 1 times negative 1 times negative 1. We have a negative 1. Negative 1 times 4 minus 2 times 4 minus 2. Again, we're just putting the x in for those x's. So that's positive 2 times positive 2. 4 times negative 1 is negative 4. And so this one would also be symmetric at negative 9. So we can go and graph our positive 1 is going to negative 1 right here. Our 0 is going to 4, negative 4, and our negative 1 is going to negative 9. And we'll have the symmetric points on this side. Whoops, right there. And right there. That one's a mistake, so let's put this one back here. All right, so you can see that it's the breadth of it is a parent function, but it opens down, so that's different than a parent function, and it's shifted to the right 2 places rather than resting right at the origin. But when you have a double root, when the roots are the same, that's what it means, is that it means that it's going to rest, okay, at the origin instead of just being above and crossing in 2 places. It'll just touch the x-axis in one place. All right, so that's the end of this lesson, and we'll go on to another.